session on our final day, where we'll be looking at challenges and advanced methods for epidemiological modelling. So this follows on from our pre-lunch half-hour session with Jane Hutton. Peter Coveney is going to do a few slides at the end of today in the discussion session. So he's going to give a bit more of a recap and a look forward then. So we're just going to press on with our first talk, but before that, I just want to remind you about feedback forms for our virtual participants. There's a link in the chat on Zoom, and for our physical participants, you've got a nice old-fashioned paper copy. We really, really appreciate your feedback, because without that, we can't improve and get better. So for our physical participants, if you could please leave your feedback forms on the registration desk later on, that would be really helpful. So without further ado, it gives me great pleasure to introduce our chair this afternoon, Dr. Kira Dangerfield, who is Senior Programme Manager for Juniper, and Kira is going to chair the rest of the session with my help.
Great, thank you very much, Jane, and welcome everyone to the final session of what's been a really interesting 3 days. And we're kicking off with a fantastic speaker. We've got Professor Veronica Bowman, who's speaking from DSTL, and it's nice to see you in person, Veronica. I saw you gave a talk in the IDP programme all about the work you've done on combining all the R numbers. So I'm really interested to hear more about the talk today about combining models in the absence of uncertainty quantification. So thank you very much, Ronnie, and looking forward to your talk.
Oh, good afternoon. I'm not going to give you any maths today. There are papers out there that will tell you about all the maths. So what you've got instead is a canter through basically what I've learned over the last 2 years, I guess. So mathematical modelling is just an approximation of reality. We talked a little bit earlier about, well, what actually is a mathematical model? All it is a representation of how we might think about what is going on in the world. And if we're talking about epidemiology, which is something that has been very close to all of our hearts for quite some time now, at its very simplest, it's literally like 3 boxes, right? With some parameters that give you how fast you move from one box to the next box and onwards. And you can get some kind of differential equations out of that. You can make it more and more complicated. And at some point, you would hope that using the basis at its heart, some epidemiological parameters, you might get at what might happen in the real world. But this probably everyone can agree on, right? It's a very simple representation of an idealized state. And every step that we take onwards from this position, whether we like it or not, is in some sense subjective, right? So why would we even bother other than as an intellectual exercise? Well, we would bother because in pandemics, we need to make decisions. Our politicians need to make decisions. Our healthcare providers need to make decisions. And they need to make decisions on things they can understand. Because if they don't understand it, their decision making will be flawed. Okay? So what are the kind of things that they understand? Well, R and the growth rate was something that got really pushed, for better or for worse. And actual realized things they understand. The number of cases, the number of hospitalizations, the number of deaths. However, when you start to dig deeper, one of the realizations I had quite early on is that deaths aren't actually deaths, right? There's about 30 different ways of defining death, okay? Because you can die of a broken leg while having COVID. Is that a COVID death? Or you can die of COVID while having a broken leg. Is that a COVID death? You can die within 28 days of getting COVID. Don't know whether we died of COVID or not, but you did. Or you can die within 90 days of getting COVID, but did COVID contribute to that or not? So even how we measure these things are completely biased effectively and subjective. Hospitalizations. Did you fall over and break your leg and go to hospital and get tested and find out you had COVID? Or did you have a really nasty chest infection and go in and that was caused by COVID? So why are you there? Did you catch COVID in hospital? Or did you have it before you went? All of these things are not simple. So let's come right back down to the beginning of like, okay, I'm a mathematician. I like things to be kind of easy to understand. So if we're going to do something with an R number, which effectively tells us a little bit about how many people might be infected going forward, because it's defined as the expected number of secondary infections caused by a typical infected individual in a completely susceptible host population, right? Now already, I'm assuming that everyone in the audience, both real and virtual, could pick about 3 holes in that statement, right? Completely susceptible host population, probably not going to happen. The expected number, well, that's going to vary. A typical infected individual, what the hell is that anyway? So it's generally defined either at the start of an epidemic or at a particular time, because it changes. And actually, there's a really good paper, plug, not written by me or anything to do with me, about all of the difficulties in working with this R number. However, if we take it very simple, right back to, well, we need some big handful stuff to help the decision makers, then you can define it as, okay, we're going to take an average across a spatial location and all potential people in that spatial location, and go on average, how many people are they going to infect? And as such, we can use it to make kind of sensible decisions about what might happen. However, to estimate that R number, we generally strive for better models. What is a better model? Is it more complex? Is it more representative? Does it have more parameters? What effectively, we're just substituting model uncertainty for parameter fitting and uncertainty derived that way. In fact, uncertainty comes in, this is my list with my kind of handful definitions, and I'm probably only scratching the surface of where all of the uncertainty comes from in any given mathematical model or combination thereof, right? If I was to properly and principled go through all of the potential uncertainties, including the unknown unknowns, I would probably get to the end and go, could be anything, which is totally unhelpful, right? So we need to make sure that we're looking at all of this uncertainty while not being overwhelmed and making sensible and principled statements. So how do we do that? It's not an easy thing to do, is it? Because you can kind of move up and down these arrows. So we could have a basic model with few parameters that in broad handfuls fits our data and fits what's going to happen. There's a few parameters I need to fit, but there's not very many, and therefore I've probably got quite a lot of data that I can fit it to. All the way up to a real world model, okay, which is actually trying to model what all of you guys are doing and everyone on the street's doing, and I've got everyone is an agent. But then I've got to figure out, well, where are you going for dinner tonight? And who are you meeting? And when are you meeting them? And what happens if actually you fall over on the way and you go to hospital instead? Like, there's so many unmeasurable parameters in that, it's just never going to happen. So should we stick with the simpler models then? Well, let's go down the other way. We've got an intermediate model. There's kind of large uncertainty, difficult to predict. But then if we go right to the simplistic models, it's not really representative of the world. It's not actually telling us anything about what might happen. It's just a kind of a big box thing that has no translation into something that you can understand, because that's not what's actually happening. So we've probably got to compromise then, and everyone will come up with different ways of modeling, and they will use different things. And maybe if we can start to combine these snapshots of reality, we can get a much better prediction of what's actually going on in the world. Because actually, every time you make a decision, use a different data stream, use a different technique, you are taking a snapshot, in effect, of what's happening in the real world. And if we combine all of those in a principled manner, or at least an open manner, so that people can yell at you about it, they yell at me a lot, then you've got a starter for 10. As long as we remember that in reality, by doing this with mathematical models, what we're actually probably combining is a little bit of a cartoon picture of the real world. We are not modeling the real world. What we are doing is providing a model representation of the real world. So it's probably a bit more like that. So this is a mathematical piece. I'm going to go through some of the ways that we might get around this. So there are different combination methodologies. They've all got pros and cons, and you really need to choose, dependent on the situation, the information you've got, which you might use. So my kind of interpretation way back when was, if I'm looking at individual parameters that I could, if I had perfect sampling, go out and actually measure, then I was going to use meta-analysis, because effectively, if I had perfect sampling and could go out, I could get a tangible thing. So meta-analysis is a way of thinking about that. However, if I have what originally were called predictions and then were actually projections, we can talk about that all day, but I don't have long enough. That meta-analysis doesn't work. It doesn't hold, because I can't actually go and measure it. You're projecting the future, right? I don't know. So in that case, model stacking will probably work better. So let's have a little bit of a think about meta-analysis then for these individual parameter values. And I'm going to stick to R at the moment. There's lots. We've already gone through why that's a difficult thing. It's a combination of real world parameters, a bit like what meta-analysis was effectively developed for, which is looking at lots of clinical trials of how well drugs work, for instance. But there is a tangible how well that drug works, right? You know, it is a thing and it will have a variation, but you know how well it works. There is also an R number out there, right? If I went and sampled absolutely everyone in Cambridge, I could give you the R number for Cambridge in a week's time. So meta-analysis gives you that consistent and repeatable way of combining model estimates. Now, the issue here is that those model estimates are all different. The variation, and I picked this graph quite carefully because actually they all lie within one another. In lots of other scenarios, what you get is something a lot more like what we saw yesterday, where I've got different model predictions all over the shop and no one agrees. So you need to do the model combination carefully. We tried lots of different meta-analysis techniques for doing that. And actually, we found that because the uncertainty bounds that we were being given on those models did not necessarily translate to what I thought of as an uncertainty bound, i.e., that tells me where the value might be, that inverse variance weight just doesn't work. Because effectively what that says is the smaller my uncertainty bound, the more likely I am to be close to the answer. If it's wildly anywhere, then I probably don't know very much. I've got a clinical trial without very much information, and that is not the case in this situation. So to kind of get at how well we were doing, we did run a simulation study. We looked at standard error, bias and skew, sampled from all of the model predictions we were given. And actually, we didn't do that bad, right? So the number of skewed and biased model estimates, you would expect that as I give you 12 models that are completely biased and skewed, then any combination I give will be a bit rubbish. Because if you give me garbage, then I will unfortunately return garbage. However, up to about a third of the models that we were getting, we were still fairly robust. I don't think that's too bad, right? Because actually, if I picked any one of those models, you know, I could be completely wrong. Whereas the combination, even if 4 of them were wrong, was giving us something a lot more stable. So let's have a look at that kind of equal and inverse weighting thing, because that got thrown around quite a lot. There are problems with equal weighting in lots of meta-analysis, but in this particular instance, where the uncertainty bounds coming out of these models are dependent effectively on how they're gathering the data. So it's sort of 3 or 4 of those different uncertainties that I introduced right at the beginning are forming them, but not all of them. That means that the correlation of how accurate they are and the width of those uncertainty bounds is effectively 0. So what happens is it's tolerant to a lot of the models being wrong, but also as you get kind of more and more correlation, you expect that black line, which is our equal weighting, dips below the inverse weighting. So what we're saying there is, as the width of the confidence interval is exactly correlated to the accuracy of the model, you want to inverse weight. But if they're completely uncorrelated, where you want to be is on that black line, because it's doing much better. It's higher up that graph. For more detailed and less whistle stop talk, go see the paper. So effectively then what you get is our combinations that we put up there going, that's what we're going to say is the combination. This is what it's done. The little grey bars are kind of what it's done in the last 3 weeks. So we're trying to give you some information. It's always shown with all of the individual model predictions so that you can do it, but it's repeatable. It's open, and it's giving you some indication of the kind of variation. She says very loosely, being a statistician, it's not actually variation at all, but some variation of what's happening. And it summarizes those models, because if I was to go to a decision maker and go, here's 8 models, crack on, they can't do anything with that. Well, which one's right? Do I just go from the bottom to the top? In some instances, the bottom was like R is 0.5 and the top is 1.8. Cannot make any decision based on that. So this gives us a way of, at least a principal way of moving forward. Can I improve on it? Yes, by all means, let's do that. However, we don't just want to do parameters. Then we need to look at combination of forecasts or projections. That isn't like meta-analysis. And there's lots of different methodologies for doing this. Now, we came up with a methodology for doing it. It's still, in some sense, equally weighted, because the issue that you have in a live situation is that people are improving these models every week. So the model that was submitted this week is better than the model that was submitted last week. So if I learn how to weight these models based on how well the model did last week or the week before, that's not fair, because it's not the same model, right? It's a better model. So I don't want to downweight that. So there are lots of ways that this could be improved, but this gives us our starter for 10, if you like. There's different ways of doing it. So we tested kind of 5 way back in the beginning. In some senses, depending on where you are, depending on what you're predicting, the combinations don't always perform as well as individual models. But if you take it as actually we need something that's repeatable and reproducible across all of the metrics and all of the locations, then that's where the combination works better. So in some instances, if you have specifically trained a model to work in a specific environment, use that, right? But if you're trying to apply a model for a specific thing more broadly, then you need to start thinking about all of the issues, and combinations get better. To help with that, so this is the basic one that's there, and it works, and you can criticize it all you like, but it's a principled and repeatable way to make decisions given data that does not rely on having to kind of group think. It doesn't rely on who had a bad day or who had a good day or what happened to my model or did it converge today. It gives you that starter for 10. We are planning to, hopefully, we've already curated the data set. We're trying to get permission to get it released, of all of the individual model predictions that we had over a 6-month period, with an easy bit to predict and a hard bit to predict in it, all anonymized with the actual data, so that we can improve on these combination methods. But my plea in my last minute of my talk would be to make sure that there will be data on COVID coming out, and it will be really easy to look back and perfectly fit it, right? But what use is that? Because if I have a new outbreak of a new variant, or God forbid, a flu outbreak, does it apply? Is it generalizable? If you've perfectly fitted it, that's great. You know, I can look at that and go, oh, I need to do this or that, the other, and fit my data, and it will all be great. But that doesn't answer the question at hand, which is, how do I help a decision maker in a situation that I don't know yet? And we had huge numbers of people literally working ridiculous amount, trying to do the absolute best that they could. And that's given us a wealth of information that we can learn from, that we can move forward from. They were all making decisions based on the information that they had at the time, the best they could. Hindsight is a wonderful thing, but don't let it blinker you into thinking that in the future, the model that fitted perfectly to the data that you had 6 months ago is going to work. So I just leave you with that. You can read the conclusions. I've given them all in the talk, but models are snapshots of reality. Make them as good as you like, make them as good as you can, but remember that. I think I finished on time.
Very much. I think the protocol is we take questions from the floor and then we'll take questions online first. So Danny, I think I saw your hand go up first.
Yeah, the thing you said about the error bars and that they're not. Oh yeah. Yeah, Danny Williamson, University of Exeter. The thing you said about the error bars, not meaning necessarily the uncertainty about the world of the particular modeler or modeling group, and not so I know of that interpretation, and I know of this is the uncertainty that this is what my model could say. Are there any other interpretations, and was there a mix of interpretations for what those error bars meant across the different groups?
Yes, there was a mix of interpretations, probably as many interpretations as there were models, because it's very easy to say this is my uncertainty bound. It is very hard to define what that uncertainty bound actually means. And I would say almost impossible for that uncertainty bound to be a true uncertainty bound, for instance, on the parameter that you're estimating based on where the real world actually is. So in some senses, the narrower error bounds that are principled on the fact that there's a very tight data stream are just as good and just as worthy, despite the fact that they may not be accounting for all of the uncertainty. But what they are doing, if they're providing, as we heard earlier, with a clear methodology and a clear definition of where their data came from and where that information is coming from and how they're generating their parameter estimate and where those uncertainty bounds come from, then I can work with that, right? Because I know where the other uncertainty might come from, and I could include another model that might be slightly biased, say, but with a better estimate of the uncertainty to try and counteract that. And I think that's where the key research in model combination needs to come from now. How do we piece together those models? It's like a jigsaw puzzle, like the picture of the world. And what we don't want is someone taking the same picture of the same area. What we want is models that cover the whole space. Does that answer the question?
Jane Hutton, University of Warwick. I was tempted to ask you to explain a bit more about slide 20, but perhaps I should do that later. This is great, trying to get people to think harder about the space and the answer you've just given. I would also in the future like people to think harder about what question are you asking? Are you just asking what happens to COVID, or are you asking what happens to the population of the United Kingdom over the next 2, 3, 5 years?
Yeah, I agree. I totally, you actually have to think about the question that you're answering and what you're trying to answer. And in some senses, you will be constrained, but I think we're also beholden in that constraint to go, you've asked me a question, I've answered it, but it's about making sure those assumptions are front and center.
Okay. Yeah, this is Dirk Groenbrunel, University of London again. I'll keep it very short. So when you're looking at meta-analysis, of course, you look at the results and the dispersion. But the thing is, a meta-analysis could be, say, 99 models of the same type, and then the 100th one is completely different. I'm just wondering, how can you quantify the differences between the way a model has been developed, and do you take that into account? Is that even possible?
So this is where the subjectivity comes in. The models that we were combining, we knew the provenance of, so we knew that they were good models. We knew that they were different, and we checked that they were different enough. So there couldn't be two identical models with two identical data streams. You would double count. There may have been two very similar models with completely different data streams, and there also may have been different models with the same data streams. And we looked at grouping those and doing sort of the two-stage meta-analysis. And actually, because of the variability in the data, I think, although it's yet to be tested, that didn't make a difference because there is such variation that it was covering the space. However, if you got to a situation where that didn't hold and you did have 99 models and they all looked really the same, then no, that's not, meta-analysis isn't the right way forward. We just weren't in that situation. But you do need to be careful. Yeah, absolutely.
One more question on the floor, then we've got two virtual questions, and the first one of which we'll go to is Mike Kate. So
thanks, James Hetherington, University College London. You said something towards the end of the talk which I thought was really fascinating. We are going to overfit for COVID, not the individual models, but our practices as a discipline are going to overfit for COVID. What should we do to avoid that?
That's a good question. I don't know that I know the answer either, other than knowing that if you're really clearly matching the data, then it's probably useful to note that any extrapolation thereof is going to be completely difficult, right? And there's statistical techniques for checking for overfitting, and there's all sorts of things, and we could do all of them, but is it going to stop us from overfitting? Probably not. I would argue that if we go with Jane's steps of being principled and we're honest and we kind of check each other enough, then maybe we can limit that overfitting. But I think we're in a world where perfect matching of the data appears to be rewarded, and maybe we need to think harder about that. There you go. It's a research topic for you.
I think we've got a question online now from Professor Mike Cates.
Hi, thank you for a great talk. So I just wonder whether a language is being developed or has at all emerged during the past 2 years, which is basically of how to describe to a non-mathematical person, such as a decision maker, policy maker, how to describe a posterior distribution. Because, you know, if you have, say, you've got two groups of models, they both have narrow error bars, their predictions don't overlap at all, then either you just make a judgment and chuck one of them out and go with the other. Or, of course, if you do classical statistics, you end up with a middle prediction, which will definitely be wrong, because all of your probability is weighted at one end or the other, and you just say, go down the middle, you're bound to get it wrong. And it seems to me that we need a way of talking about this in a sort of understandable language, that maybe the weather forecasters are beginning to get, like you say, oh, well, there's 30% chance of rain in the next hour or whatever. But I just wonder whether you found that beginning to emerge, or whether it's something we still need to work on pretty much from scratch.
I think there's ways of getting these things across that someone can understand. And that isn't necessarily by using very principled language. Sometimes you just need to get the idea across. However, I think that the last couple of years have opened more research questions than I have ever seen. So you're right, we are looking at kind of areas where model combination of two things puts us effectively right in something that is utterly preposterous, right? And we've been wrestling with this for a long time. So when I started looking at uncertainty way back when, it was just around the time that there was a big prediction of snowfall over New York and they closed New York. And then there wasn't very much snow and everyone was like, well, they got it wrong. And actually, some of that was about model averaging, because one model said not very much snow and one said lots and lots of snow. And if you average that, you got something that didn't happen, right? Because it was one or the other. You're right, you have to throw one away. But I would argue then that what we need to do is go back to our definitions of uncertainty, go back to our model combination techniques and actually look at, well, what do we do when we've got a multimodal distribution, and how do we combine things, and how do we think about this, and how do we translate that? You know, we've got a probability yardstick of almost definitely, very likely, likely, not likely. Well, what does that really mean? And everyone has a different assessment of risk. And how you visualize that is an open question, and how you communicate that is an open question. But I think it's beholden on us as mathematicians to start that, because I would hope that we are probably best suited to understand what the numbers mean, and we have to start that translation process.
So I think we've got one final question. Hopefully it's a quick question from Ian Vernon online.
Hi. Listen, thank you for a lovely talk as ever. Just to follow up on that sort of debate, in the UQ community, we spend a lot of time talking about this structural model discrepancy, which is this explicit acknowledgement that the models are incorrect or off based on their assumed model structure, in addition to all the other uncertainties. So this gives you a nice framework to tell you when you should say average models equally, or when you should weight one more than the other, because exactly what you're hitting into there are inaccurate descriptions of uncertainties, which are perhaps ignoring the model component of this. So again, Mike's example of averaging two quite disparate predictions and getting something in the middle, well, if you have a more deeper structural uncertainty understanding, that would lead you to not do that, to have a sort of wider uncertainty on this. So would you suggest that groups sort of look into this? Because there's a whole list of sort of techniques to assess structural model discrepancy, which range from sort of simple to quite complicated. So is that the sort of direction you would advise we go in?
In some application areas, yes, I definitely think that's the way to go. In this application area, I personally struggle to see how you're going to get a handle on model discrepancy when the models change weekly, because your estimate of model discrepancy will also change with the change in the model. So if you've got kind of a static model, or even a model that is similar, self-similar, then I think model discrepancy is a massively useful tool and one that should be developed. But if the models are literally changing and they're adding in more data streams and they're changing the data streams and they're kind of structurally different, then I struggle to see how you estimate that model discrepancy, which doesn't mean you can't, because there are lots brighter people than me working on it. But then I start to worry about how we do it.
Thank you.
Great. Thank you very much, Veronica. It was a really interesting talk and lots of interesting